Can you guys hear us?
Hello, can you hear us?
Okay. Yeah.
Okay, now you can hear us. Welcome, everybody. Sorry, we had a bit of a mic issue in the beginning. Can you all hear us?
Yeah.
Okay, great. So we do have a few people here in person, and for those that are in person, help yourself with the pizza and the drinks. And there's also enough maybe to take out later for friends and other lab mates. I think since we are like 3 minutes over, maybe wait 2 more minutes and then we get started. We're going to record this as well so that afterwards you can then also watch it again. And we'll also make that recording available on our website. Okay, welcome everybody. My name is Sabina. I'm one of the organizers of this very cool autonomous racing competition, which will be blended in a sense. We have a first stage that's virtual with a simulated setup, and then we do have a physical race in Perth. And I'm one of the organizers. Sabina with me is Willis, and James is the third team member. I think he's online. Couldn't make it because of in person because of a last minute demonstration. But we're not the only one behind this. We are representing here AIDA and Perth, but there's also the Wilson Center for Advanced Computing with Eric in the team, and that racing competition is also supported by our partner Wind Races, which is a large manufacturer of a fixed-wing drone, and you see one of those drones that they manufacture here on the screen. I think we can get started, right? Can I walk you through what we're going to talk about? First of all, I'm going to give an overview of the competition, the task, and the deadline, and then Willis will take over and walk you through the simulator. It's really recommended that you actually then also log in and just follow along so that you get all the details. Talk a little bit about the sample solution and then question and answers about the competition, timeline, scoring, and etc. This is a racing competition, but the focus of this racing competition is the design of guidance, navigation, control algorithm for fixed wings. And you see here on the screen the vehicle that you would be, dealing with. And for that vehicle, you would have to develop an algorithm. We will provide you with a sample solution. And that is a race. And the race is going to take place in Perth, which you see here on the screen. And some of you might know it if you're from Purdue. If you're not from Purdue, then we'll also, brief background. Perth is the largest indoor motion capture lab, size of a football field, and it's equipped with motion capture technology, active and passive sensors, so that we can actually get the ground truth data. And you will work in teams, and it's a race. And the fastest lap time around a specific flight test area will define who's going to win it. And there's also prize money. We also award prizes, and we also get certificates. And I want to give you a bit of heads up. This is the first stage of a competition, and we have developed a new simulation tool here that we'll be using. We'll plan to go international afterwards next year, and then having more team members participate. So I just mentioned that we'll have two stages. First is the virtual stage, and you see here, that's the simulator we'll be using, the ROS2 based simulator. And again, fixed wing UAV is the focus here in terms of the dynamics. And Willis here next to me has worked on the simulator that you will be using. And then the phase 2 is the final teams. I think the final 5 teams will go into phase 2, where you will then perform a physical flight. And go on. There was just someone, I think, trying to log in. I don't know if I have to help out here. I think Willis is taking care of. The structure of the competition, it's team-based, up to 5 participants. We plan to have about 25 or maybe 50 teams in this competition. There will be one person handling the online submission. So in terms of the account, there will be one person representing that. You can for sure in the first phase, as we are working on, simulate on your own, but eventually will be one person handling the submission online. You will submit online, and you also do have to follow a format structure, and Willis will lead you through. So these are minimum requirements you have to fulfill. If you do not fulfill those requirements, we cannot score you. We will actually release a leaderboard also, and then you can see how you perform. And I think in about 1 or 2 weeks from now, we will start actually releasing these scores, so they can go online and also check your score. What is the prerequisite? It would be good if you know a little bit about guidance, navigation, control. It's also good if you have a bit of experience in ROS2, Python or C++ programming. And for sure, also learning a little bit more about fixed wings. If you have worked on fixed wings, I think it's not a problem if you've worked with rotor-based drones before, but what might be your first experience with fixed wings. I guess this is just like just an overview of the setup. We are using here our own RCC Getter system. It's basically out-of-the-box setup. You go online, you can simulate, we show you that. You basically have a desktop version that you run in the cloud. You can also use construction, and that's what we have used before in prior competition, or you can run a local installation. You have these 3 options. We would appreciate if you use the RCE Getter system. Why is that? We are trying to develop that further. As part of that project, it's, by the way, supported by a Digital Innovation Initiative of Purdue University. We are trying to improve also our simulator in terms of the photorealistic nature of it. And the winning teams will have access to that new version of that simulator, and would like to use that phase also to collect feedback. So use the system, because we actually want to learn from you and see what we need to improve. I think now I'm going to hand over to you, Willis. He's going to walk you through, give you a bit of detail about the competition, and then actually show you the solution.
Yeah. Thank you, Professor. Yeah, so I'll go over a little bit about what we would do on a little more the technical and the ruling and the scoring side. So as Sabina has just said, we will be evaluating based on the best lap time for the competitions, and we'll take your best lap time, calculate it into a total score with a penalty of if you do any violations like corner cuttings of the given pylons, or you fly out of bounds of the accepted flight test zone, then we'll accumulate all those penalties and give you the final time score. This is the timeline that we have imagined for this first iteration of the competition, where we're here right now on the info session number 1, and in about 2 weeks we will be releasing the final the Pylon course that we want to do on the virtual side, and also the scoring architecture for you to submit your solutions and get evaluated on, and get an updated leaderboard moving forward. We'll do another info session after that release to address any questions or any help that you may need to clarify from us. With the phase 1 deadline targeting on December 1st. So with that, you submit your sample solution for the virtual round. From there, we'll choose the finalists and then advance them to phase 2, where you deploy your algorithm that you have tested on the virtual side on an in-person real vehicle at PERT. In terms of the reward, we have a simple cash prizes for what we want to do for this round, where we take 5 finalists and they'll be awarded based on the following cash prizes. Yeah.
Certificates. We'll get those as well.
And we will also provide certificates for anyone participating, and we'll have a trophy for the winner from the final phase 2 round in person. So now moving on, I can go over a little bit on the webpage and how you can access the simulator online through the RCAC's GEDIS system. So just give you a minute to scan this QR code so you can follow along. And yeah, we can go over how you can set it up and get access to that simulator.
For those that are online, so if you just go to the website right now, directly log in, I think it will be useful to follow along as Willis is now showing you how to do that.
Yeah. Let me go ahead and also paste the link here in the chat so that you can easily access this as well and follow along. Okay. Yeah, I realized the QR code maybe be not working, but yeah, you can access the link here on the chat. Okay. Yeah, we can keep going then. So once you access this overview page of the competition, we have all of our outline details of what you may need, what are the key deadlines, and we'll relay any information, any updates through here. And some of the FAQs that we have published, you can view all these directly from this page as well. So to access the simulator, we also ask you to register your interest here on the link. It will take you to a survey that you can give your contact information so that we can reach out regarding any further updates, registration, or any, or etc. So once you do that, we have this login link here at the top right. You can log in using your Google account. So once I log in here using the Google account, I can select go to the competition portal. And then if I launch the simulation, it will take a couple of seconds here to boot up on the RCAC's GEDIS system that we have set up. So I think there's a question, how do we get the login info? So to log into the system, you would only need your Google's Google's account to log in. So once you log in using Google, you should be able to access this simulator. There's no other login info that you need to get access to this. Yeah, feel free to let me know if you still have an issue accessing. Yeah. Are there any further questions now, or if not, I can go over the setup of what we have here on the desktop app. Yeah. So once you access here, like once you access this web browser-based simulation, you can see some of the file structure here that we have set up. Just a regular desktop with an extra folder here called Pylon Racing. And in here is a ROS2 workspace that stores every file that we have to run the simulator and as well as the sample solution. For you, before we go into the file structure of how I've set up the sample solution and the simulator, to simply test the current solution, we have set up this button as well, that if you click on that run ROS2 simulator, you should be able to see this Arvis like rendering comes up. And all of this are done based on ROS2 and also Python-based integrators that we have set up here at Purdue. And you can see the baseline solution running for the fixed wing simulator that we have set up to closely resemble the Sport Cup vehicle that we showed earlier on the slides. Okay. So yeah, let me go through in terms of the file structure and what you can do to make adjustments to this or to like make your contribution or write your own controller to work with this solution. So if you navigate to the workspace, and go to the UAV Pylon package, we have set up this VS Code so that it is a little easier to work on your code edits. In this package, there are three main files that we have. There's a ROS2 script, there's a controller script that we have, a Python-based controller, and here's a navigation controller. And all of the parameters that are being used on the simulators are all in this YAML file that you can access here as well. So one thing to note that once you make any changes to the YAML file, you can rebuild your ROS2 workspace and then also run it and see how that changes your vehicle control in real time. And for those that are planning to write your own controller to work with this simulator is providing you with all the odometry messages from the simulator that we have. And all you need to do is to publish this auto join message to provide the control to the vehicle. And then, yeah, so I can go over some of the details in terms of the sample solution, what algorithm is being used for reference if we have some time later today as well. Yeah. Yeah, if there's any questions that you have right now, or if you have any issues running the simulator or the sample solution, we can try to address that right now as well. Feel free to let me know. Yes, yeah, yeah, that's a good point. So in terms of the question was if we have any set of instructions or something that you can access. So the workspace that I was showing is the is a sample solution that I've created. There's a whole README file that you can go over basically what we have gone through today, including some of the message definition, how each messages are being run, and how each joy controls are mapped to the vehicle input commands. So I can link this here right now as well. But it's, yeah, we clone it from this main repository, and any updates on the parameters or any to address any questions, I'm happy to keep that repository updated with any like further adjustments as well. Mhm. Yeah. If you don't have any questions right now, we can go back to the slides and we can move forward from now. So to go over how you can participate in the competition, we mentioned a little bit about like navigating to the web page. What we would imagine you can submit your final solution is you can fork this sample solution package that I have included in the chat, make any adjustments or add any files that you may need for your sample solution, making sure that you're publishing to any topics that the simulator is taking. And then from there, we'll have our evaluation script that will run your sample solution. Well, that will run your code solution, and we'll evaluate your lab time from there. And then we'll be releasing some of the agreements forms and any like official registration to the competition in like shortly as well. Yeah. Yeah, so I briefly go over the structure of the sample solution, but this outlines how the sample solution is being hooked together. Mainly, we have the input flight mode. We set it on the simulator to be automatically set to auto. So it would listen to any auto input that you give it. And then the vehicle would then react based on that autonomous like joy command that you feed it. The other input that we have in this sample solution is a waypoint-based navigation. So we have the control points, waypoint that we set. It will feed into a navigation scheme where that navigation would feed the desired tracking points for the controller. So right now the controller is using a PID-based controller to navigate around the course. And that PID controller would then compute the commanded joy messages to the UAV, where UAV would then close the loop by giving the position and orientation messages back to the controller as the current state. And also here we have a waypoint checker to check whether or not the vehicle has reached a waypoint. And then it would command the next iteration of the waypoint. So this is how the current sample solution is being structured. And you guys are more than welcome to improve upon or completely redesign the entire guidance, navigation, and control logic as well. Yeah, so just to link it back to how we imagine we would deploy it to the real vehicle. So once you have that set up, it is being set up such that it will take in the same type of messages to control the real hardware vehicle. So in terms of the hardware vehicle, we have this off-the-shelf like Pylon Hobby Sport Cup S2. So it's around 60 centimeter wingspan, if I remember correctly. But it's a vehicle that is fast enough and also durable enough that you can safely test within the indoor motion capture facility at PERT, where we outfit it with this active marker control board. And this little blinking LEDs would then blink a certain infrared frequency so that the cameras can detect each of the markers and identify where the vehicle is in space and what their orientation is in all within the indoor space. One thing to note is on the real deployment, you'll be getting 100 hertz of motion capture ground truth that it goes up to 3.5 meters. Anything beyond that, you could occasionally lose tracking, so you may need a filter to go into a more advanced realm if you choose to fly in a higher altitude. And all of these details will be published once we get closer to the in-person phase, so you'll be aware of the limitation. And yeah, so in terms of feeding the control to the vehicle, I mentioned here we have a 10 hertz discrete control sampling. So all of the codes, all of the guidance, navigation, and control algorithm logic will be done on the ground. So we have this laptop that we can clone all of your solutions in, or you're very welcome to bring your own laptop to the testing site. We connect it with this Arduino Nano ESP32, and we use the proprietary LimonRx transmitter to directly feed the control messages to the vehicle. So how this works is we have this RC controller that we use for safety that we can take over in manual if it were to fly at someone that would compromise the safety of anyone and PERT. But essentially we'll try to keep it into auto as much as we can. But that control command script will go into the autopilot laptop. Autopilot laptop compute any control algorithm, control logic that it is running, serialize that messages into the Arduino, where the Arduino would then pack all of those serialized control commands into a single strand of signal, feed it to the LemonRx, LemonRx to the vehicle, and we can close that loop using the motion capture system in PERT. So all of this are done with this respective rate. So just to keep in mind, and when you design the controllers, that would be your limitation in terms of what you can feed to the vehicle. Yeah. So yeah, that concludes some of the overview that we have. We have the link here to the Discord channel that you can address any like quick Q&A throughout between now and throughout the competition time. So I'll try to monitor that and try to answer to any of the questions as promptly as possible. Yeah. So we hope this QR code works for the Discord channel, but if not, please let me know. We're happy to share that later as well. Yeah, and we still have some time over, so I can go over some of the details of what we're using, like the technical detail of what we're using for the sample solution as well. So if you're interested in learning more about what we're doing in terms of the sample solution, please feel free to stay. And all of this recording will be shared. So if you missed the meeting, we'll be sharing this entire recording as well. Yeah. Yeah. So If there's no immediate questions, we can go into a little more of some of the technical detail, how we set it up, and we can move forward. So there's a question that, do we need to bring our own platform? No, you do not. We can provide any platform that you may need, both on, well, from the virtual phase, you can log in on your web browser, test any algorithm, make any changes to the sample solution, or to create your own solution, participate all from your web browser. For the phase 2 in an in-person flight, we can provide all of the any laptops that you may need. We can clone your solution, run it without having to bring your own platform. But you are very welcome to bring your own platform as well, if that is easier. Mm-hmm. Yeah. In terms of just to dive in a little bit more on the simulator architecture, I mentioned briefly that there are 3 main packages to run our solution. We have the sample solution here using the AUAV Pylon 26 repository. We have the cup description, which includes the robot model description, where you can see all of the renderings and the transformation of the robot on the simulator. And finally, we have the Sayaka. Sayaka is hosted, is part of the CogniPilot autopilot environment that we have here, and we run all of the integration, the ROS2 based simulation through the single package called Sayaka. In terms of the architecture, the figure on the right goes over what we have set up for the simulator. So I mentioned a little bit about the flight mode switch. You have an option of plugging in your standard like USB like PC controller onto your laptop as well, where we have a flight mode switch that you can control that manually, or right now it's default so that it would accept like the autonomous control. Once you have that flight mode switch, it passes through the Casati automatic differentiation tool, take in any state parameters that we initialize with the vehicle, and we put it into a fixed wing dynamics at 6 degree of freedom fixed wing dynamics, initialize any initial states, and we have this Sayaka kinematics doing orientation based on quaternion coordinate system, and a 3-dimensional positional system. We use the Casati integrator to update any states all within this Sayaka environment. And then in terms of ROS2 messages, we have the robot description, as I mentioned here on the COP description package. And we have any TF transformations linked into the RBIS2 visualizer that I was showing on the simulator. So that's the simulation. In terms of the sample solution and how we handle the guidance and navigation side of the control, guidance and navigation side of the solution. Here's the diagram that I briefly mentioned earlier. We have the navigation and the waypoint checker logic. Right now, we have the input of the control waypoints, and we use the basic course track deviation navigation base. As you can see here is a contour of the desired heading of the vehicle. So the vehicle would be commanded to face the trajectory waypoint and intercept the trajectory using this cross-track based logic. So no matter where it is in space, it will try to converge to the reference path here, as you can see here on the plot. And in terms of the longitudinal desired glide path control, we use the desired glide path based on the UV position and the desired waypoint altitude, calculate the glide path to intercept that waypoint. So that's the basic logic that we're doing for the guidance and navigation side of this. And moving on to the control side, as some of you may know, fixed wing dynamics has a lot of challenges in the control reversal phase, where, for example, when a fixed wing is flying at low speed, it would use throttle to control its altitude and use pitch angle to control its airspeed. But when the fixed wing vehicle is traveling fast, it would be the reverse, where you would use pitch to control the altitude and the throttle to control airspeed. So with that discontinuity in control, it is challenging to use the simple PID logic to accurately control the vehicle without inducing stall or handling that like discontinuity in the control gain reversal. So with that, we are motivated to use this control system called total energy control system. What it does is, instead of leveraging pure thrust desired or pure like speed desired, we would then use a total energy based approach, where the throttle would be used to either add more energy to the system or remove energy to the system, where the pitch would then use for allocation of those energy into either potential or kinetic energy. So this diagram kind of highlights that base logic of the total energy control system, where let's look at this green region over here, that if you are at trim, or if you're here and you want to increase the altitude while decreasing speed, you would then command a down elevator control so that the vehicle would pitch up and go in this green region. On the other hand, if you're doing the blue region here, where you want to decrease the altitude and decrease the speed, you would then command a less thrust control to get into that region. So this total energy control system is very nice in handling this region of reverse control for fixed wing. And therefore, we are using this for the longitudinal control of the fixed wing vehicle as a reference sample solution. In terms of the lateral heading control, we are using the just basic PID based control to track the desired heading. And then one thing to note, here's the equations that are being used on the sample solution as well. This represents the total energy control system. Yeah. So that's what I have so far in terms of the sample solution on the technical side of how it's being routed together. I'll be happy to take any questions now, or yeah.
Here from the back, I don't know if you can hear me, but if there are any further questions, either share them now here in the chat, or go to the scores, and as I've typed here, or email us, and we'll try to also add more tutorials and more info as we are going forward. Thank you, everybody. Yeah. The recording will be online. We'll also share that with the people that are here in the call and that have signed up on the website. And spread the word as well. So we look for more participants. So if you have classmates or friends, lab mates that are potentially interested and haven't heard about it, please spread the word. We want this to be very exciting.
Yep. Yeah. Thank you everyone for your time, and yeah, please let us know if you have any questions. And as Sabine said, feel free to advertise this to anyone and encourage people to join and participate in the competition as well. And yeah, we are very excited to host this and then see people get excited for the fixed wing UAV moving forward.
Thank you, everybody. Thanks for joining. Spread the word. We'll see you soon online or in person. We will have another info session coming up as well. Thank you.
Thank you.
Thank you, everybody.